Alright, in 11.3, we're going to talk about the one of the biggest things in calculus, which is the tangent line problem. And we're going to start by looking at approximating the slope of a graph using a tangent line and using the limit process to find the exact slope of a graph. So things that we know about slope. We know that slope describes the rate of change of a line, and if it's a line, every point on the line has the same slope. The problem that we run into is if we have a curve, so like x squared, x cubed, square root function, anything like that, the rate of change at a point, it changes, the slope changes depending on where we're at on the line or the curve. So it turns out we can use the tangent line to approximate the slope. Remember that a tangent line crosses through a graph only once. It actually can cross through more than one time further out in the graph when we talk about in behavior. But we're going to be using tangent lines to estimate slopes, and they're important because in calculus we use rate of changes to look at applications in real life functions. Alright, so in this first example, for a, I have the function f of x equals x squared, and I want to find the slope, or approximate the slope at the point 1, 1. So I'm going to find my point 1, 1. And I'm going to draw a tangent line to that point, and that might look something like this. So there's my tangent. Remember, it can't cross through, it's just going to touch and then keep going. So if I have my point 1, 1, and I find another point that looks like it maybe crosses about right there, my rise and my run, looks like I run 1, I rise 2, so my slope would be 2 over 1 or 2. So my slope of the graph of x squared at 1, 1 is approximately 2. Very similarly for b, f of x is equal to negative 2x cubed, and I want to find the slope at 1, negative 2. So I found my point 1, negative 2. And then I'm going to draw my tangent line. And that might look something like that. So there's my tangent line. And then I'm going to estimate my slope with my rise and my run. Go over 1, down 1, 2, 3, 4, 5. It looks like it might be between 5 and 6. 5.5-ish. So my slope is about negative 5.5 over 1. So my slope is about negative 5 approximately. Remember, we're approximating, so it doesn't have to be exact. We're just trying to get an idea of what our slope might be. So approximating is great, but what we really want to do is find the actual slope. And we said before that the slope can be found by finding the slope of a tangent line. So if we imagine some curve, so some random equation, we don't know what it is, but we've got a curve, and I want to find the slope at this point right here, which we'll call x, f of x. So I've got my function f of x, and then I've got a point that I want to find the slope of that tangent line. Well, we know to find slope, we need 2 points. I don't have 2 points, I have a single point. So what we start with, in calculus what you start with is you find the slope of a secant line, which is a line that crosses through a graph. So if I pick another point here, and I give that a value, and we'll call that, we don't know where it's at, we just know that it's that x value, and if we add some h value to that, so we have like this new point x plus h, and then we have f of x plus h. That should kind of look familiar to you guys. I can find the slope of that secant line. But that's not a very good approximation because I've got all this waste space in between here. So what we want to do actually is get that h value, this change, as close to our original point as possible. So if you can imagine, if I take that h value and I move it down a little bit, this secant's a little bit better. If I move it down a little bit more, that secant is a little bit better. If I keep moving it down until that h is like as close as it possibly can to that dot, I get really close to a tangent line. Well, that whole process sounds a lot like finding the limit of a function. Remember we said a limit of the function was what happens as our graph gets really, really close to some value. And it turns out that we can use this difference quotient along with our idea of slope to find the slope of the tangent line. So if we take the 2 points that we have, let's plug them into this formula right here. Okay, so y2 would be our f of x plus h minus y1 would be f of x divided by x plus h minus x. So that's our slope between some fixed point and some other point on the graph as well. So we have that, and if we do a little bit of work, we get f of x plus h minus f of x divided by these x's are going to cancel out. I'm left with h. Well, that's going to give me the slope between any 2 points, some fixed point x and some point that's h units away from x. And what we decided we want to do is make that h value as close to 0 as possible. Like we want that distance between x and h to be as close to 0 as possible. So our difference quotient is going to be this function, f of x plus h minus f of x all over h. And we want to evaluate that as a limit as the h value goes to 0. And that's exactly what we described, or what I described when I was finding those secant lines, is I want the h value to be as small as possible, which is exactly what we're doing with this limit. And that right there, that limit as h goes to 0 of f of x plus h minus f of x all over h is the difference quotient, which is what we can use to find the tangent line at any point on a graph. Alright, so how do we use it? So right here it says find the slope of the graph of f of x equals x squared at the point negative 2, 4. Well, we just learned that the slope is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, if we plug in some things that we know, so the limit as h goes to 0 of f of, what's the x value that we're looking for? We want to know what's the slope at negative 2. So it's f of negative 2 plus h minus f of negative 2 all over h. And now we did this a couple days ago. We had a function. We didn't know what we were doing. We just knew we could do it. We had some quotient, and we're going to plug into a function, x squared. So we've got the limit as h goes to 0 of, let's see, f of negative 2 plus h, so that's x is squared, so that's negative 2 plus h squared minus negative 2 squared all over h. Remember, this was just x squared and this was just x squared. Alright, so we've got that. Now we can start evaluating it or simplifying. Can't plug in 0 yet because it's still undefined. So I'm going to expand this out. Negative 2 plus h squared is 4 minus 4h plus h squared minus 4 all over h. And then we can see that the 4's cancel. So now I have the limit as h goes to 0 of negative 4h plus h squared all over h. And now each term has an h, so I can cancel one of those out from each. And left with the limit as h goes to 0 of negative 4 plus h. Now I can evaluate it. Remember, we're going to evaluate it at 0. So h goes to 0, so that whole thing goes to 0. So my slope is negative 4. So the slope of that function, x squared, at negative 2, 4, is negative 4. And if we verify that real quick, here's the graph of y equals x squared. There's 0, 0. Negative 2, 4 is going to be up here. Think about drawing that tangent line. And yep, that would make sense that we would have a slope of -4 at that point. Alright, so let's look at this one. Find the slope of the graph of f of x at equals 5 over x at the point 5, 1. So that right there is the x value that we're looking for. So we're going to use our difference quotient, limit as h goes to 0 of f of 5 plus h minus f of 5 all over h. Remember the difference quotient was limit as h goes to 0 f of x plus h minus f of x all over h. So now we can actually plug into our formula or our function. Limit as h goes to 0 of 5 over 5 plus h minus 5 over 5 is just going to be 1 all over h. Common denominator, we're just going to multiply this left hand side by 5 plus h over 5 plus h, or the right hand side I should say. Just the limit as h goes to 0 of 5 minus 5 plus h all over 5 plus h, that whole thing over h. So I just I simplified this top complex fraction into one big fraction. Don't forget your parentheses. So that leaves me with the limit as h goes to 0 of, see these 5's are going to cancel, I'm left with negative h over 5 plus h all over h. And we saw on Friday that those will cancel. So I'm left with the limit as h goes to 0 of -1 over 5 plus h. Now I can evaluate it when h goes to 0. That goes to 0, so that's done. So I'm left with -1 over 5. So the slope of the function 5 over x at 5, 1 is -1/5. Alright, and one last one. So again, find the slope of the graph of f of x. This time it's equal to the square root of x minus 6 at the point 10, 2. So again, difference quotient, limit as h goes to 0 of f of x plus h minus f of x all over h. We want 10 is our x value that we're plugging in for. So the limit as h goes to 0 of the square root of 10 plus h minus 6 minus the square root of 10 minus 6 all over 2. So again, this first part here was f of x plus h. This is f of x. I don't know why I said 2. That should be over h. Sorry about that. Alright, so now we start to simplify. The limit as h goes to 0 of the square root of 4 plus h minus the square root of 4, which is just 2, all over h. Now we're going to use our conjugate, so we're going to multiply the top and the bottom by 4 plus h plus 2 over radical 4 plus h plus 2. And that's going to give me the limit as h goes to 0 of 4 plus h minus 4. Remember, when you multiply by the conjugate, you square the first term, square the last term, put a subtraction between them. We're just doing the difference of squares. So it's a squared minus b squared is what we did there, all over h. H times, sorry about that, h times the square root of 4 plus h plus 2 on the bottom. Alright, so now those 4's cancel, and I have the limit as h goes to 0 of h over h times square root of 4 plus h plus 2. Now those h's cancel, and I get the limit as h goes to 0 of 1 over radical 4 plus h plus 2. Now I can evaluate it when h is 0. So direct substitution, that goes to 0. I get 1 over the square root of 4, which is 2, plus another 2, which is 1/4. So 1/4 is the slope of the graph of radical x minus 6 at the point 10, 2.